Hello, everyone. So today we're gonna start little mini unit on analytical or analytic geometry. It's really nothing too crazy. It's just the union of typical Euclidean geometry and algebra. So, um, a little bit of historical context. Ancient Greeks, when they were doing geometry and numbers and things like that, were expressed in geometric terms. So, um, like the number two would be like the length of a segment that was twice as long as a segment of length one or something like that. They wouldn't really sort of think of it like we do with um, the Hindu Arabic number system. Uh, so that happened for a long time. If you go and read some of the ancient like Greek textbooks like Euclid's Elements, you won't see a lot of numbers, but you'll see stuff like Euclid proved um, there's an infinite amount of prime numbers, but he did it in such a way that he expressed those prime values in terms of lengths of segments. And then later on, when algebra became more and more developed, we started working with numbers and stuff like that. And then this guy, Rene Descartes, comes around and creates what we know as analytic geometry, fusing algebra and geometry together. So it sounds complicated, but all it really is like, okay, we're using a coordinate system now, which you probably have seen plenty of times before. This is called the Cartesian Plane on the right because it's named after Rene Descartes. It's all it is two number lines put together. The x-axis is a number line, the y-axis is another number line. Each number line represents a dimension you're working with. So since we have two number lines, we're working with two-dimensional lines, shapes, things like that. Every sort of place on this coordinate plane is represented with what's called an ordered pair. So an ordered pair is giving us the location of a point relative to the origin. Now the origin is where both the y-axis and x-axis intersect, right there in the middle. As an ordered pair, your origin has a value of 0, 0. It's like the base default starting point of all the things we'll be working with. So, to pick another point, like if the exact middle is 0, then if I have a point out here, we would write it out like this. So this point from the origin has moved 3 spaces to the right of the x-axis. So on the number line, that would be like a 3. The 3 would be the first number in our ordered pair. And then we look at how far along it traveled from the y-axis relative to the origin. Well, it moved up 2 spaces, so that's our second number in our ordered pair. So this point I marked would be the point 3, 2. The first number represents the x value. The second number represents your y value. Pretty simple stuff. Here's some more of that. We got, like I said, 3, 2. You can move in the negative direction, in the number line. Like, think of a basic number line. If I move to the left from 0, those are my negative numbers. So on our x-axis, we can see I moved 5 spaces to the left. That's why this x value is a -5. I also moved 1 space down, so that means my y value is -1. So again, all these coordinates are just telling us the locations of these points on our Cartesian plane. All right. Negative. When your x coordinate's negative, it means the point is to the left of the origin. If your y coordinate is negative, then it's below the origin. Yada, yada, yada. Went over this already. Okay. Sometimes you can have points that are neither above or below one of the axes or the origin or whatever. So like this point 4 comma 0. That 4 means okay, move 4 spaces to the right on the x-axis. And then since my y coordinate is 0, it means I haven't moved up or down relative to the origin. It stays put, so again, it doesn't move up or down. And likewise, with that coordinate 0 comma negative 3, well, that negative 3 means I go down 3 spaces on the y-axis, but that x coordinate of 0 means I don't move left or right with respect to the origin. I just stay put where it is. All right, what else? Okay. We aren't restricted to using integers. Integers are whole numbers. It just means with the coordinate system, we're allowed to use decimals, negative numbers, even fractions if you want, but you don't see fractional numbers in your ordered pair too often. But it could happen. But when you do only have integer values in your ordered pair, that means it's called a lattice point. And you can tell a point is a lattice point if it ends up on like one of these intersections of the, lines in the grid. So the one I just marked as a lattice point, over here we got a lattice point, but that original point that right here is a non-lattice point because it has those decimal values, and you can even see it's not at one of those intersections on the grid. Okay. I think. Alright. So, the importance of these graphs aren't just for points, because points are interesting, but they won't get us everywhere we need to go. So, we're going to build the next step up. Just like in Euclidean geometry, the next step up from a point is a line. So, we can graph lines on the Cartesian plane using equations. These equations have variables like x and y, which means we can input multiple values in for, like, let's say x, and because of that it'll alter the value of y. So we get, as a result, all these different types of ordered pairs we could possibly imagine. For example, this line that we see on the graph is represented by the equation 2x plus 3y equals 6. Now, how do you know? Well, let's just take any point on this line. I'll start easy with let me mark it in red. Here. This point is 3 comma 0. 3 comma 0. So, how does that point work with the equation that we're given? 2x plus 3y equals 6. Well, my x coordinate is a 3. So if I take this equation and substitute a 3 where my x value is, and then I also notice, okay, my y value is 0 on that red point. So where I have a y in that equation, I can substitute a 0 in. And that should all be equal to 6, if the math works out. Well, 2 times 3 is definitely 6. 3 times 0 is 0, so that just is going to cancel out. So yeah, 2 times 3 is 6, and that is certainly equal to 6. So I know that red point right there is a valid point for that equation, and therefore belongs on that line, as you can see. If I picked a point that was not on this line, like over here in blue, so that blue point I just marked would be negative 2, positive 1, negative 2 comma 1. Now let's try and see what those values would get us. So again, I'm going to take my equation 2x plus 3y equals 6 and since my x value on that blue point is -2, I'll replace the x with a -2. -2. Plus 3 times the y value, which is just 1. And if this was a valid ordered pair, this should all be equal to 6. Well, -2 times 2 is -4. And 3 times 1 is just 3. Which is equal to, well, -4 plus 3 is -1. Which is definitely not equal to 6. So it means the result doesn't make sense. -4 plus 3 is not equal to 6, so that point -2, 1 does not work for our equation, and that's why it's not on the line that we drew. And we'll kind of dive more into this in a second. But whenever you see a line, it's the result of what's called a linear equation. A linear equation just means the highest exponent on one of your variables is a 1, or really just don't see an exponent. And again, we'll dive into some more of that stuff later. Usually, you'll see linear equations in written out like this: ax plus by equals c. That's called standard form. It's just a nice way to kind of like, represent some of these lines, although we will see different types of these equations, linear equations, later, different forms for them. Okay, alright, this is all messed up. Hold on 1 second. Alright. So, with our lines, we'll get what are called intercepts. So, where our line crosses or intercepts the x-axis, that point is called our x-intercept. So if I look at this line, it crosses the graph at the x-axis at that red point. So that means my x-intercept is going to be the coordinate, and we can see that is 3, 0. Again, because that is where our line crosses the x-axis. Well, then we have the y-intercept, which is where our line would cross the y-axis at, and that's going to be this point in blue right over here. That's where our line crosses the y-axis. So our y-intercept is going to be equal to the coordinate 0, 2. Very cool. Okay, and then we have what's called the slope. The slope sort of determines the direction that our line is going in, and we can use this formula to determine what our slope is. M is our slope. M is just the letter we use for slope. And we can find that by taking 2 coordinates and subtracting the y values, and then dividing that with the difference of the x values. Let me see. Let me just move ahead real quick. Okay, so I'm going to do that here. I'm going to erase all the x-intercept stuff since it's in that paragraph anyway. But I'm just going to show a quick way we can sort of calculate the slope of this line. So m is equal to y2 minus y1 over x2 minus x1. Well, I'm just going to take any 2 points. Might as well take the intercepts. Intercepts are very easy to work with. Our 2 intercepts were 3, 0 for the x1 and 0, 2 for the y-intercept. And I can really just sort of, it doesn't really matter which one I call x1 and x2. Just keep it consistent. And what I mean by that is, if, let's say this is my x1, then the coordinate next to it would have to be my y1. I couldn't just say it's x1, y2 in the same ordered pair. That doesn't make sense. So I'll just call the ordered pair 3, 0. That's going to be my x1 and y1. And then our next ordered pair 0, 2. That will represent my x2 my x2, and my y2. Okay, so just plug those values into our formula. Y2 minus y1, so my y2 is 2, minus my y1, which is 0. And then over x2, which is 0, minus x1, which is 3. And we're just going to reduce that. So we got 2 minus 0 is just 2, and 0 minus 3 is negative 3. Now, usually when you write this out, it's kind of just more common to put the negative with the numerator, but it really doesn't matter. I'll show you why in a second. But, this would be our slope. Our slope is negative 2 over 3. And the reason that works is because if I take, let's say this point right here. Let me do it in blue. This point right here. The slope determines the steepness and the direction of our line. So the numerator determines how we're changing in our y value. So if I'm using this slope, I'm going to go down 2 spaces in our y direction. And then the positive 3 in your denominator represents the change in your x value. So I would go 3 spaces over on the x axis. So altogether, I would go down 1, 2, and then over 1, 2, 3. And look at that, we end up with another point on the line, and we can just keep doing that over and over. So if I take this point again, go down 2, over 3, hey, we end up here, down 2, over 3. That's why the slope is so useful, because it gives us a string of points that we can sort of go along and plot out. But what if instead I used, if I wrote it instead as 2 over negative 3? Well, it really won't make much of a difference because, all right, let's take, I'm going to change it to red this time to show the difference. So here's a point on our line. Now if I do 2 over negative 3, again, that numerator represents the change in my y value. Since 2 is positive, I would go up 2. And that negative 3 in the denominator is the change in my x value. So that means I'm going to go to the left 3 spaces. Because again, negatives on our x-axis mean move towards the left. Think number lines. So with this red point, I'm going to go up 2 and to the left 3. And hey, wouldn't you know, I end up at this point. And again, same thing. Up 2 to the left 3. And there we go. So it really, you can write it both ways. I just tend to write it with the negative in the numerator. Just, I don't know, I think it's more standard. But either way, it will show you the direction your line should be moving. The steepness and the direction. If you have a positive slope, your line should be going upwards if you're looking at it from left to right. And if you have a negative slope, it should be going downwards if you look at it from the left to right. You can see the examples, the positive slope on the left, negative slope on the right. And even if we go back to this problem where we calculated the slope, we can see the slope negative 2 over 3. Hey, that's a negative slope. And once you look at it, that line is going downward. It's because it's a negative slope. So again, positive slope means your line is going to go upward. Negative slope means your line goes downward. And then I believe this is the last one we're going to talk about with slope for a little bit. The magnitude of your slope determines the steepness of your line. And what I mean by that, the magnitude, the greatness of the number you're using. So the smaller the less of magnitude your slope is, the less steep your line is becoming. So if my slope is 1 over 4, we can see the lines, it's going up and up, but by a very small amount. If my slope is 1, hey, it's rising a lot faster than that previous one. And if my slope is 4, it's really steep. It's 4 times the steepness of that one in the middle. You can see it's rising like really, really fast, basically. So again, that magnitude is determining the steepness of the line that we're getting. So hopefully that all makes sense. That's it for this video. In the next video, we'll sort of cover how to actually deal with some linear equations, figure out how to build linear equations with pieces of information we're getting, and all that. And we'll go over some of the different forms linear equations can take. So I will see you then.